Okay, let's double see what's going on. I'm streaming. There we go. So here we are. 1, 2, 3, 4, 5. See if anybody shows up. Okay, so I'm here in case anybody have a question. Some people have been asking me what's the range of the topics for the exam, and so the exam is actually up to chapter 8, from 1 to chapter 8, and yes, chapter 9, which we just started, which includes hypothesis testing, is not on the test. I shouldn't call it an exam, it's more of a test. So that's kind of where we are with that. So if there are no questions at this time, then I could perhaps do a sort of a slight review of a couple of things. Let's see. Let's start with the chapter 1, which is data types. So with chapter 1, data types, we often talk about 4 types of data. And the 4 types of data would include nominal, ordinal, interval, and ratio data. So nominal data is just categorical data that has no particular hierarchy to it. So everything is sort of treated equally. And that would be, for example, if I could just simply put people in groups or categories. If I could say, if I just were to name objects in a room and there's no particular hierarchy, then that's just nominal data. But if I now use categories, but the categories have an order to it, then I call that ordinal data. So for example, if I ask you what year are you in your first year, second year, third year, fourth year? These are categories, but the categories have an order to it, so that would be ordinal data. And then interval data is data that has characteristics of ordinal, but it does not have an absolute zero. By that I mean that on the scale, zero does not necessarily mean that whatever it is that you're measuring does not exist. So for example, temperature has a 0 point, but it doesn't mean that temperature does not exist. It just simply means that we've set a reference point for temperature that we will call 0. Another one, another example could be if I'm using a customer satisfaction rating system, and I've decided that I'm going to rate from -5 to +5. So where the 0 is like a neutral satisfaction rating. So it doesn't mean that satisfaction doesn't exist, it's just that I'm neutral. So +5 would be I'm ecstatic, and -5 would mean that I'm really, really upset, or I really don't like the service. So in that case, if I go from -5 to +5, the scale has regular intervals. And the differences make sense. So for example, if there's one interval between 4 and 5, then there is that same interval between 4 and 3, and 3 and 2, and so on. That's interval data. But the 0 is not an absolute 0. It's a reference. Ratio data, however, with ratio data, the 0 is an absolute 0. So if we're talking about, if we're talking about, say, weight or height, if we have 0 height, then whatever it is that we're measuring does not exist. And then the ratio also makes sense. So if something is 4 feet tall, and we have another that's 2 feet tall, then one is twice as tall as the other. So in that case, we do have the ratio making sense, and the 0 is actually an absolute 0. Okay? I see I have some people joining me. If you have questions, please feel free to type your questions. Could I do the question on the workbook, chapter 7? Question 37, page 327. Okay, let me see if I could find that question. All right. Give me 1 minute. I will try to find that question and try to bring it up. So let's go back here where I have all my files and try to bring that. Okay, bear with me for a second while I try to retrieve that question, okay? Oh boy, this is slow. Come on, come on. Maybe, I'm not sure why it's going so slow. So, okay, I got my questions now. Let's see what we got. Number 7, page 37. Number 37, sorry, chapter 7. Just loading up. Okay, so let's try to find this question. Let's see here. Okay. Peter's chapter 10. We want a question on chapter 7. So let me get back to that. It's chapter 9. chapter 7, question 24. So it must be coming up here now. Let's see. 25, 37. There we go. All right, so need to put on my glasses. I should, shouldn't I? Okay. People end up tossing 12% of what they buy at a grocery store. So that came from the Reader's Digest, March of 2009. Assume this is a true proportion, and that you plan to take a sample survey of 540 grocery shoppers. Show the sampling distribution of P-bar. Right? So first of all, we're told that people discard 12% of what they buy, and we want to take a sample of 540 grocery shoppers. Show the sampling distribution of P-bar. So when it says show the sampling distribution of P-bar, what it's asking you is to basically provide the parameters of that sampling distribution. So if I could write right here. So here is what we believe the population proportion to be, 12%. Because it said people end up tossing. We didn't get that 12% from a sample. People end up tossing 12% of what they buy at the grocery store. So that's population proportion P. And then we have a sample of 540 grocery store shoppers. So what happened is that because we're dealing with population proportion, whenever we take a sample proportion, the sampling distribution of the sample proportion could be a normal distribution. But before we decide to claim it as a normal distribution, we need to test whether or not the conditions for normality are satisfied. So we know that we could use a normal approximation to the binomial if P times N is greater than or equal to 5. So P in this case is 12%. And if we're looking at 540 grocery shoppers, I'm pretty sure that 12% of 540 is greater than 5. If we just take 10%, 10% is 54. So 12% is even higher than that. So that's satisfied, and therefore 88% is also going to be larger than 5. So we have the conditions met for normality. So when it asks to show the sampling distribution, what it means is that we need to put the mean of the sample proportions will be the same as the population mean, and the standard error of the sample proportions will be P1 minus P over root n. But in MindTap, if you were doing this question in MindTap, you would need to put the actual values. So in this case, P is equal to 0.12, and then we would have to compute what the sort of value is right here, which is, so I would have to compute sigma P bar, and put in 0.12 times 0.88 over 540, which is what we want. Whatever that turns out to be, that's your standard error. So we now have the mean and the standard error, okay? And those are the two parameters for the sampling distribution. So the second part of that question asks, what is the probability that your survey will provide a sample proportion within 3 percentage points of the population proportion? Well, the population proportion is 12%. So if I want to be within 3 percentage points, so 0.03, then it means that I'm looking to be between 12 plus 3 makes that 15, 12 minus 3 makes that 9, between 9 and 15%. So essentially what we want to do is we want to be within P plus or minus 0.03, but P is 0.12, plus or minus 0.03, which means that the upper probability, proportion should be 15% or 0.15, and the lower would be 0.09. So essentially that's kind of what we're looking for. We want what is the probability of being in that range. Okay? So to get that probability, I'm just going to set it up. I don't have my calculator with me to work the details of it, but you could certainly finish that up. So that would be my 0.15, that would be my 0.09, and this is 0.12. So I would need to find the corresponding Z values to the 15% and the 9%. So let's call them Z2 and Z1. So Z1 will be associated with the 0.09, Z2 with the 0.15. And so Z1 would be 0.09 minus 0.12 over the standard error, which is 0.12 times 0.88. Let me just make that a little clearer. 0.88 divided by 540. So whatever that turns out to be, you'll get this Z value. It will be a negative value, negative some value. And of course, because the 15 and the 9 are equidistant from the mean, whatever the Z value turns out to be, Z2 will be the positive version of that. And then you simply need to find the area between those two, you need to take A2 minus A1, AZ1, sorry. AZ2 minus AZ1 would be the probability. Because AZ2 will give us all of this area under the table. AZ1 will give us this area under the table. So when I subtract my orange area from the green area, I will get the area in black, which is what I'm looking for. This is the area that I'm interested in. All right. So to wrap this up, the probability that P bar is between 0.09 and 0.15 will be AZ2 minus area associated with Z1. And you could compute what those values are, and that would solve the problem for you. Okay? Let's go back and see what's the second part of that question. Third part of that question. We ask, let's see here, sorry. What is the probability that it will be within 5%? That's the same thing. So 5% would mean 5 plus 12 is 17. 5 from 12 is 7. So between 7 and 17%. If you could do B, you could certainly do C. What would be the effect of taking a larger sample on the probabilities? The effect of taking a larger sample on the probabilities, what will end up happening is that your standard error will get smaller. If you look at the formula for the standard error, right here, what will happen is that if I take a larger sample, say 1,000, my standard error gets smaller. If my standard error gets smaller, then what happens is my Z values get larger. So as my Z values get larger in this case, I should have more area between those points. Let's just see if we could illustrate this for you. So let's assume that this is the original distribution and I'm here. These are my 2 points. So what happens is that the area between those 2 points, let's call this P bar 1 and P bar 2. So in part B, it was 9 and 15. In part C, it would be 7 and 17. If I now increase the sample size, what happens is that the standard error decreases. So my curve actually would change. Let me see here if I could use a different color. So my curve would change. So what happens is that when that curve gets smaller, because of the smaller, let me see if I could do this over again. Maybe a little nicer. So with the smaller standard deviation or standard error, Notice now that I have less area in the tail. If I now have less area in the tail, what would happen is that I now have more area in between those values, more area of the curve. So the probabilities will actually increase, is what's going to happen. All right? The probabilities will increase. Okay, so that answers the question. I see I have another question, which is chapter 8, problem number 29. Let's take a look at that question. So chapter 8, problem 29. Here we go. So the travel to work time for residents of the 15 largest cities in the United States is reported in 2003. Suppose that a preliminary simple random sample of residents of San Francisco is used to develop a planning value of 6.25 minutes for the population standard deviation. If we were to estimate the population mean travel time for San Francisco residents with a mean error of 2 minutes, what sample size should be used? Okay, so basically we want to do some planning. We expect that the standard deviation, and in real life, you really can't necessarily set that up. But anyway, you want it to be 6.25. All right. So we want to estimate the mean travel time. We want to estimate that mean travel time to work with a margin of error of 2 minutes. We want a 95% confidence level. So what sample size do we need? So what we know is that the margin of error, whenever we want to compute an interval estimate for population mean, is given by Z sigma over the square root of n. That's the margin of error. So in this case, we want to be within 2 minutes, I believe it was, plus or minus 2 minutes. And we want a 95% level of confidence, which means our Z value is 1.96. And the standard error we told was 6.25. That's not standard error, but standard deviation. And we don't know what sample size would give that to us. So now we could compute what our sample size should be. All right? So n is equal to 1.96. When you manipulate or do the algebra, 6.25 over 2 squared. Whatever that turns out to be, that's your answer. Right? And I'll let you calculate that value. So that's the first part of that question. Let's see what the second part is. If we want to estimate the population mean travel time to work with a margin of error of 1 minute, what should we use for the same level of confidence? Well, we're just repeating the same question, except now instead of 2 minutes, we're now changing it to 1 minute. So here's what we did for 2 minutes. In this case, if we want 1 minute, then simply all we have to do is to say n is equal to 1.96 times 6.25 over 1 squared. And of course, notice what will happen is that the sample size will increase significantly, I believe, because now we want to actually reduce our margin of error to much lower than 2. We're going to go from 2 to 1. Since your margin of error is going to be smaller, then you will actually end up with a larger sample size that you need to take. Okay? Very good. Jana, how are you? So that's great. Let's see. Any other questions? So I've had 2 so far, which is good. I see somebody wants me to look at, is that the same? I've already looked at this one. Number 29 on chapter 8. So, anybody else? No problem, Brandon. You're welcome. Anybody else has a different question? If not, let me see what's challenging people. I just want to mention to you that we've been doing stuff on hypothesis testing, and hypothesis testing, whenever we calculate a p-value, that p-value, another term for it is really probabilities. And I just want to mention that the work that we did in Chapter 7, finding probabilities with proportion or probabilities with the mean, those are actually p-values, but we didn't call it that in Chapter 7. But in the context of Chapter 9, those very same probabilities are really p-values. And p is really stands for probability value. So just something that I wanted to mention. So those were two questions on sample size. One of the things to remember, sometimes you may have a problem where you're trying to estimate the mean mu, and your initial sample was small. Let's say you had a sample of 25, and you use the t distribution, x bar plus or minus t s over the square root of n. So while that was your margin of error in that interval, if we now want to estimate the sample size for a different margin of error, we will not use t s over root n as the margin of error. We will use the z. You replace t with z, and there's a reason for that. The reason for that is t is a function of the sample size. And because we're trying to calculate the sample size, we do not yet know what t is. Or we do not yet know what the sample size is, therefore we won't know what t is. And so therefore we cannot use t, because t is a function of the sample size. So in that case, we need to just replace the margin of error with z is equal to s over the square root of n, and then we could compute n is equal to z s over ne all squared. Okay? And so always remember that. Even if you start off with a small problem, sample problem, and now we ask you to calculate the sample size for a given margin of error, you need to use z and not the t. Okay? Good. Let's see here. Anybody wants me to explain some other concept that might be a little bit challenging for you? Let me just mention a couple of things while I'm waiting for a question. So one of the things about statistics that will really help you to understand it well is to learn the language. The language is very, very important. So if I say, for example, sampling error, that's one that a lot of people tend to forget. So what is sampling error? If I'm trying to have a population parameter, say for example mu, or even p, whenever I take a sample statistic, so in this case for the mean will be x bar, for the proportion will be p bar, the difference between my sample estimate and the population is an error. And so that's what we call sampling error, because it came from the sampling process. So x bar minus mu is a sampling error in this case, or p bar minus p is a sampling error in this case. All right? So I just want you to keep that in mind, that sampling error is the difference between the statistic and the population parameter. And so when you look at a z value, for example, a z value, that is the sampling error expressed in standard deviations. This is the standard error, sigma over square root of n. So that there is the standard deviation of the sampling distribution of x bar. So I'm taking the sampling error and I'm measuring it in standard deviations. So what happens is that whenever we do things like hypothesis testing and we get a large z value or t value, essentially what we're saying is that your estimate was so far off, right? The sampling error is very large when you have large z's or large t values. And when the sampling error is very large, it means that the sample estimate is not representative of that population parameter. All right? So something to keep in mind in terms of the importance of learning the language. So standard error, sampling error, the standard normal variable, which is this here, the t variable, or the t value. So all of those things, p-value, what is p-value, type 1, type 2 error, all of those terms are very important, all right? So a couple of quick formulas just for revision. It's important to just kind of remember your formulas. Everybody know how to find the mean, sample mean, sum of the x's over n, right? Standard deviation, S, if we're finding sample standard deviation, which in most cases that's what we're looking at. You'll notice in the formula sheet I have SSX over n minus 1. But then SSX is defined as, in your textbook, it will be this. Xi minus X bar all squared. Which basically what it stands for is the sum of the x's all squared. Sum squares of the x values. So SS is the sum of the squares. But I don't want you to use this formula. I want you to use the shortcut formula. X sum of the x squared minus the sum of the x all squared over n. That would be my SSX. And then we put that SSX in the formula right here. Now some of you may be more comfortable. We've actually seen the formula complete, which is S is equal to sum of x squared minus sum of x all squared over n divided by n minus 1. Some of you might be more comfortable seeing it that way. That's fine as well. All right. So that's standard deviation. That's the mean. Finding coefficient of variation is just the ratio of the standard deviation to the mean. And so CV is just sigma over mu for population, or S over X bar for sample. And we usually express it as a percentage multiplied by 100%. Okay? So that helps us to say the coefficient of variation is 40%, 50%, 60%. It basically means that the standard deviation is 60% of the mean, or 40% of the mean, and so on. So that's kind of all we mean by this. So that's kind of a bit of chapter 3 when we get into some descriptive statistics. We have a formula for covariance and for correlation coefficient. So now when two variables are involved, so covariance basically is looking at the relationship between two variables. Okay. Just before I continue, I see a question. If the margin of error increases, will the sample size increase? No. If you think about it, whenever you want a small margin of error, you need larger sample sizes. So larger sample sizes give you a smaller standard error, and that smaller standard error times the critical value, Z or T, will make it smaller. If I keep on increasing the sample sizes, my standard error gets smaller, so the margin of error gets smaller. But if I reduce the sample size and make them smaller, then what happens is that my standard error will get larger. When my standard error gets larger, the margin of error also gets larger. So the way it works is that large samples give you smaller margins of error. Okay? Hopefully that answers the question. So getting back to covariance. Covariance is the relationship, looking at the relationship between two variables, how they vary. And so we usually have X and Y. And one is usually dependent on the other. So X is an independent variable, Y is a dependent variable. So we could think of, for example, age and height. So people get taller as they get older, and of course after a while they stop growing. But age and height in the early stages should have some kind of relationship to each other. So we can measure the covariance by taking X minus X bar times Y minus Y bar. Okay? And then if we divide this is sample covariance. If we divide this by n minus 1, That is sample covariance of x, y. But then let me just give you the shortcut version of that. So we could replace this numerator by SSXY, which looks like this, sum of x times y, minus the sum of x times the sum of y over n. So that's the shortcut version of that. So anytime you have a problem, you have the x's, you have the y's, all you need to do is create a third column with your x times y, and then you'll be okay with that. So that's the the sum of squares xy, and that's our covariance formula. Now the covariance formula can be negative, unlike the regular variance of x and variance of y cannot be negative, but covariance can be negative. If it's negative, it means that x and y are negatively related. If it's positive, it means that x and y are positively related. Okay? Now, one of the ways of measuring that relationship, the strength of the linear relationship, is through something called a correlation coefficient, which is rho. Rho is between -1 and +1. If it's +1, that means that a perfect correlation, positively correlated. If it's -1, it's perfect negative correlation. All right? And we calculate the sample correlation or population correlation coefficient as follows. So let's use rho for the population correlation coefficient. It will be the covariance of xy over the standard deviation of x times the standard deviation of y. All right? That's how we would do this. And that gives you the correlation coefficient. Now, that's the one that the textbook uses. I actually have one that's slightly different in the formula sheet, which is our shortcut version, and I would recommend you use it. It goes like this: SSXY over the square root of SSX times SSY. And please note that SSX is not the same as S of x, which is the standard deviation. This here is standard deviation, those values, but this is not quite the standard deviation. That is the sum of the squares. We need them to calculate standard deviation, right? So for example, the standard deviation of x is SSX over n. If it's population, then it would be n. We have to take the square root of that. So these values in here are the sum of the squares, but these values up here are the actual standard deviations themselves. Trust me, this is less work than this right here. So if in case you have to do a calculation involving covariance, I recommend that you use the shortcut formula on the formula sheet. And so SSXY, I've already written it before, but I'll write it again, is sum of x times y, sum of x times sum of y. That's it. Over n, sorry. SSX will be sum of the x squared minus sum of the x, and we square the whole sum of the x's. And we divide by n. And then SXY is similarly sum of y squared minus sum of y, the whole thing squared divided by n. So those are the formulas that I recommend that you use. They will definitely be a lot easier to work with than actually trying to work with the formula that the textbook gives you. So that covers chapter 3. Let's go to chapter 6. I'm just quickly reviewing some of the key formulas that we have in those various chapters. So chapter 6 is just basically finding the normal distribution. And we showed you that anytime we're interested in probabilities under the normal distribution, then we simply use the formula z is equal to x minus mu over sigma. Now, one of the things that I've noticed in the past with some students is that because we've been doing a lot of stuff related to sampling distributions, and sometimes when we put a question together that is just a regular normal distribution question, they're looking for a sample size. They're like, where's the n? Where's the n? Well, remember that we still have not gotten rid of just the plain normal distribution. So if I ask you a randomly, if I say, you know, in a particular neighborhood or at a particular restaurant, people spend an average of $50 a night with a standard deviation of $25, right? What's the probability that a randomly chosen person has spent $70 or more? So you go x, probability of x greater than or equal to 70 is what I'm looking for. So there's no n to look for. That n is just one person. But if I ask you what's the probability that a random sample of 25 individuals has spent an average of $70 or more, now you're hearing a random sample of 20 people spending an average of $70 or more. Now we're talking sampling distribution, and I'm interested in the probability of x bar greater than or equal to 70. So instead of this formula now, I'll be looking at using Z is x bar minus mu, which is the sampling error, over the standard error, sigma over the square root of n. And that will be my Z value, okay? So I want us to just kind of remember, we could flip back and forth between just there's a plain normal distribution and the sampling distribution. Cool? All right. So that's chapter 6 and a little bit of chapter 12. Chapter 7, what we covered in chapter 7, basically we were looking at sampling distribution of the sample mean, sampling distribution of the sample proportion. So sampling distribution of the sample mean x bar. So a sampling distribution basically is created by taking repeated samples from a population. It has a mean mu, standard deviation sigma, and if I keep taking repeated samples, I will get x bar 1, x bar 2, x bar 3, etc. So all of those, when I put them together, will have a sampling distribution where I could take the average of all the sample means and the standard deviation of all the sample means. And we have a theorem that says if the population standard deviation is known, then that sampling distribution is normal with a standard error of sigma over the square root of n and a mean that is the same as the population mean. All right? And anytime we're interested in finding probabilities under that curve, then we would simply state the probability of the random variable, which is x bar, being greater than or equal to some value, or it could be the probability of x bar being less than or equal to some value. This is an x bar 0. Or it could be the probability of x bar being between x bar 1 and x bar 2. So we could find any of those types of probabilities. All right? We could find the probability of being exceeding a value, probability of being lower than a value, or the probability of being between those values. Okay? Those are the three options. Now, we could also find probabilities with, hello Sanjay, how are you? We could find probabilities with the t-distribution. So what if sigma is unknown? What happens? Well, if sigma is unknown, my sampling distribution will be a t-distribution. So now I have to assume the population is actually normally distributed. And now I'm using t. All right? So t is my random variable. And so I could still find t is equal to x bar minus mu, but notice s over the square root of n because I don't know sigma. If I knew sigma, I would not need t, I would only need z. All right? And I could now find probabilities that x bar is greater than some value. And if sigma is unknown, then I must use the t value right here. So based on the t value and the degrees of freedom, I could actually find the probabilities. Now, unfortunately for us, in our table, we have a limited range of probabilities that we could find. Because remember, the way the table goes is that we have the degrees of freedom, 1, 2, 3, and so on. And then we have areas in the tail, 0.2, 0.1, 0.05, 0.025, 0.01, 0.005. So whenever we compute that t value right here, we must look at the respective degrees of freedom, try to find that t value, and then go up here and read the area. Chances are we won't find that t value in the table, so we will end up writing our probability as a range. We are between this value and that value. But let me just mention that if you're good at using Excel, then you could actually get the actual value. And I believe the function in Excel is tdist. So if you put equal tdist, it will ask you for your t value and your degrees of freedom, and also the mean. You could use the t value and degrees of freedom, and will give you a cumulative one. There's another one, I think that might be inverse, sorry. T inverse, I believe it's. But then the t distribution, tdist, I believe would be, and I have to confirm that. The good thing is that Excel will give you what parameters you need to provide. I think you will have to provide the mean, the standard deviation, and the value of the x value that you're interested in, right? And it will give you the exact value. But for our table, you will end up giving us a range of values. Okay? So that's sampling distribution, where you're finding probabilities, but sigma is actually unknown. And just hold 1 second. My computer's about to die on me. Let me just plug in my computer. Please bear with me for a second before it dies. Battery life. Hang on, because if the computer dies, the stream shuts down. I only have a couple more minutes, about 10 minutes. If anybody has a question, please fire away at me. Otherwise, I'll just finish up the formulas for the chapter 8. Chapter 7 and chapter 8. So that was basically finding probabilities involving sample means, all right? And if sigma is known, we use Z. If sigma is unknown, we use T. Now, what about proportions? If we're interested in finding probabilities involving proportions. So what happened again? We generate a sampling distribution for the sample proportion P bar. And when the questions in your text and so on ask you to show the sampling distribution of the sample proportion, all it wants you to give is what is the mean of that sampling distribution, and what is the standard error of that sampling distribution? Well, we know that the mean of P bar is the same as the population, and the standard error of P bar is P1 times 1 minus P over N, and we take the square root of that. So that's all we need to provide. So now that we know the mean and the standard error, we could actually find probabilities under the curve. Now, we are assuming here that the sampling distribution is normal. Why? Because we have a normal approximation to the binomial that says if n times p is greater than or equal to 5, and n times 1 minus p is also greater than or equal to 5, then we could use a normal approximation to the binomial. And that normal distribution will have a mean of p and the standard error of P1 minus P over N, all right? And the square root of that. So once we have that, if we're interested in finding probabilities under the curve, then we will need to calculate our Z value and go to the table. What's the formula for the Z value? All the Z values have the same basic structure to it. That we have Z is equal to the sampling error, which is P bar minus P, divided by the standard error. And we could expand that to show P P bar minus P over P1 minus P divided by N. And that's our Z value, all right? And we could use that to find probabilities and so on. So that is finding probabilities with the sampling distributions. And those probabilities are the same probabilities we use in Chapter 9 in hypothesis testing. Those are p-values. So I could ask you a question where you would have to find the probability of p bar greater than or equal to some value. Or I could ask you p bar less than or equal to some value. Or p bar being between p bar 1 and p bar 2. Your book likes a lot of those questions. What's the probability of being within 5% of the population proportion or 10% of the population proportion? So a lot of those questions were actually asked. And you simply need to now go ahead and calculate the two Z values. You'd have to find Z1, which is associated with P bar 1 minus P over sigma P. And then you need to find Z2, which is P bar 2 minus P bar, minus P, not P bar. Here we go. Minus P over sigma P bar. Once you find those two Z values, if you are interested in the probability of being between two values, you must subtract the areas associated with those Z values. So then it becomes, that probability would be the area associated with Z2 minus the area associated with Z1. Right? And then last but not least, in Chapter 8, we talked about interval estimation. So we did interval estimation for mu. The interval estimation for mu requires that we have to have a sample estimate. Our sample estimate would be x bar. But we must add and subtract to that a margin of error, which is made up of a critical value times a standard error. So our point estimate, critical value times the standard error. So if sigma is known, it is sampling distribution is normal. That's what our critical value comes from. And we say Z alpha over 2 because alpha is a significance level, and that significance level is in the tails. And so we must split alpha between the two tails. So if it's a 95% confidence interval, the significance level is 5%. That is the probability the interval does not contain the parameter, which is the population parameter, the mean mu. And so 2.5% would be in each tail. And for that, the Z value would be 1.96. Since we know sigma, the standard error would be sigma over root n. All right? So we know for 90% confidence interval, Z is 1.64. For 95% confidence interval, Z is 1.96. And for 98%, it's 2.33. And for 99%, it's 2.58. You could memorize those. If you memorize those, then this means it saves you a little bit of time having to go to the table. And so that's the case where sigma is known. What happens when sigma is unknown? If sigma is unknown, then we have the following. X bar plus or minus, we use a t distribution. And it will be t alpha over 2, but there's a degrees of freedom associated with that. So t alpha on 2 degrees of freedom, and then of course we use s over root n because sigma is not known. Right? So that's our critical value, which is t, and that's our standard error, and that's our point estimate. All right? Same idea over and over again. And with those, whenever we want to find sample sizes for margin of error, we know the margin of error is Z, either sigma over N or S over root N, which gives us that the margin of error is Z sigma over, sorry, not the margin of error, sample size. We manipulate the formula, we're doing a little bit of algebra, and the sample size is this. If we don't know sigma, then we will replace sigma by S, sample standard deviation. Okay? For proportion, our point estimate is this. Our critical value is Z, and the standard error, which we talked about earlier, is P 1 minus P over N. But I cannot use P because I don't know P, since I'm trying to estimate it. And so therefore, I must replace this with P bar. And then that gives me the confidence interval, Z alpha over 2. And then now if I want sample size, it turns out that the margin of error is the Z into P bar 1 minus P bar over N. Square root of that. So we can manipulate the formula to make N the subject of the formula, and we will get sample size is equal to Z squared P bar 1 minus P bar over NE squared. That's the formula. And all we're doing is we're just squaring both sides. Square this side, you get rid of the square root sign, so the Z becomes Z squared, but then P bar into 1 minus P bar over N comes out of the square root, and when you make N the subject of the formula, then we would end up bringing the margin of error to the denominator on the other side, and we would get that as our formula. So there you go. That's how you would actually find the sample size involving proportions. All right. So that's pretty much it. The main formulas that you need from chapter 1 to chapter 8. Of course, finding the median, you know, is just half of n plus 1, right? And then, if it is a whole number, great. If it's not a whole number, then you have to average the two middle numbers. And pretty much you do the same thing. 1 over 4 for quartiles, n plus 1. For third quartile, 3 over 4, n plus 1, and so on. If we want percentiles, then it's just percentile over 100 times n plus 1. Okay? And that will give you a percentile. So I think that covers it all. The mode we know is most frequent value. Median we know how to find. Mean we know how to find. Standard deviation. All of those things. All right? Good. It's 9:15 now. I have to shut down. I have to shut down because I do have to go and pick up my daughter from dance. I see a question from Catherine. Are the questions we've done so far similar to what will be on the test? I would say they're similar in that they cover exactly the same concepts. Right? They're not the same questions with the numbers changed, but they cover the same concepts for sure. All right? Good. Good luck, everybody, and good night. And thank you for tuning in. And I'll see you over the weekend. I'll be monitoring things over the weekend. Hopefully no one will have any difficulty. You're expected to do your tests on your own. It's open book, so you'll have access to the formula sheet that I gave you, or formulas in the textbook. And remember that once you start, the clock starts to tick. And you cannot pause, go away for 2 hours and come back. Your exam will not be waiting for you. It will be automatically submitted. Okay? Thank you very much. See you guys soon. Take care. Bye-bye.